Okay, in this video, we're going to look at how to create one of our spreadsheet calculators for doing hypothesis testing of two independent samples and two independent means, averages, when we actually know the standard deviations of the populations from which those samples came. Very, very rare that this happens in the real world. This is really more of a learning tool to kind of see how we can transition from dealing with two independent proportions to two independent means when the standard deviations are known, because both of those tests are on the z, the normal curve. And then we'll transition in later videos and later studies to dealing with two independent means when we don't know the population standard deviations. And that just forces us onto the t-curve instead of the z-curve. And the t-curve, as we all know, is pretty much identical to the z-curve, especially as the degrees of freedom gets larger and larger, i.e. your samples get larger and larger and larger. The t-curve ends up looking just like the normal curve, but it's slightly different for smaller samples. So back to this example, where we've got two samples, 1 and 2. Now, these two samples are the same size. That's just a coincidence for this particular example, because these are independent samples. There's no relationship between the two samples, so they don't have to be the same size, because these are two different sets of objects that are being measured. In the case of this example, it's how much weight one group of people lost over 3 weeks versus another group of people that were on a different type of diet over that same 3 weeks. And we're basically just testing to see if the diet had an effect, right? Because if we assume the two groups are equal in all other aspects that would influence how much weight you lost or didn't lose, and if we control for all of those other factors, and the only difference between the two groups now is one has, the new diet and one has just the old diet kind of thing, then if we do see a significant difference between the two, we can say, aha, it's got to be the diet that's making that difference, because that's the only factor that was really different between those two groups. Remember, and that's basically how hypothesis tests work. If you can control for everything other than one factor, or sometimes it can be a combination of factors, and then you test to see if those two groups differ on some sort of measurement, whether it's a mean or a standard deviation or proportion or whatever, then if you see a difference between those two groups and you've controlled for everything other than this one little factor or this one little group of factors, then when you see that difference, it kind of tells you, it implies that, well, then that factor is probably the thing that is making that difference. You'll notice I say probably, right? We're not really proving anything until we do these rigorous, experiments where we have control groups and a controlled environment and blah, 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 blah. Okay, so enough about that. Let's get back to creating our calculator. Just as a reminder, this is the formula for our z-test statistic, and we're doing z's again because we know the standard deviations, so that's why we have little sigmas, right? Because those are the standard deviations of a population, the Greek letters. And when we know that, then we're going to get a z instead of a t. Some of the stats that we're going to need to calculate, right? We're going to need the sample size of both groups. So there's sample size of the first group, sample size of the second. We're going to need to know the mean of both. So there's the mean of the first, the mean of the second. Here's the standard deviation of the first population, right? The sample came from, and the same thing for the second. Then we're going to look at the sample difference. That's just mean 1 minus mean 2. That basically just gives us the number that would be in the top of this formula. Then we're going to calculate this actual z-stat using Excel language or spreadsheet language. And then we're going to calculate our p-values, whether it's a one-tailed test or a two-tailed test. Okay, as before, if you've watched any of my other videos about creating calculators, I always color cells in yellow to indicate a cell that I have to manually put a data value in. And then the things that don't have yellow in them are values that the spreadsheet itself calculates for me automatically. So when I come over here and I change my data, all the numbers over here will change except for the ones in yellow. Because in this particular type of scenario, we're supposed to know the standard deviations of the two populations. And so we have to put those in. We have to say, okay, well, here's the known standard deviation of the first population. Here's the known standard deviation of the second population. Here are my two samples, right? Up here, sample one, sample two. And if I put in this data, it's going to calculate everything else and it's going to spit out a result. Okay, well, how do we get all this stuff? Well, the sample sizes are easy, right? That's we're just counting up everything that's in column Q, and then we're taking the average of everything in column Q, and then the same thing down here, right? We're counting up everything in column R and taking the average of everything in column R. Now, of course, you could have your data in different columns, so instead of R colon R, it would be A colon A, or whatever column has your data. And then, of course, these are just numbers that are typed in. Okay, the sample difference, that's really easy. We're literally just taking the difference of our two means, so that's why it's T4 minus T7, right? Because again, I'm in column T, you could be in something else. So there's 4 minus 7. Right? If I click up here, you can see where it highlights, it's the blue one minus the red one. So that's pretty simple. And then we have to recreate this formula in Excel. So because I already have a cell that has the difference, I don't have to worry about having like parenthesis, T4 minus T7, close parentheses, divided by the square root, blah, 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 blah. So I can just have this T9, because that's where the difference sits. And the reason why I do this is because a lot of times you'll be doing some work, and one of the questions that you'll have to answer on a homework or a quiz or a test is, what was the actual sample difference? So there it is, right? It's calculated for me each time. So I'm going to do that, T9 divided by, and then of course in our, don't forget you have to start with an equals, right? Every time you have it do something, calculate something, you got to start with an equals. So equals T9 / for division, and then SQRT, that's always the function notation, right, for doing a square root in any kind of spreadsheet. An open bracket to tell it we're going to do square root of all the stuff that's inside here. And then we're just recreating this, right? We need our population standard deviation squared. So there's T5 caret for raising it to a power of 2 in parentheses, because it needs to know that I'm just going to raise it to this number, and then when I'm done, I'm going to divide by T3, right? Because T5 was this yellow bit that I know, and then I have to divide it by the sample size, which is here in T3. Then I'm going to add, and I'm going to do the same thing with the other group. So there's my T8 caret 2 divided by T6, because in this case, I now want the standard deviation of the second group squared and then divided by the size of the second group. So it's a fairly basic formula. It's not that difficult. It's not that hard to type this stuff in, and then now it will do our z-stat for us every time, and we don't have to, if we're putting in numbers, if we were just typing in the values here instead of the cell references, we'd have to retype those in for every new homework or quiz question. Okay. One of the kind of nice little handy shortcuts that I've shown in other videos, and if you haven't seen it, you'll see it here again, is whenever we're doing the p-value of a one-tailed test, we have to make sure that we're always using the test statistic that would be on the high side, right? We need the positive value of the test statistic, because we're using the norm.distribution function, and the norm.distribution function always gives us the area under the curve that is below, that is to the, below something. Oof, I'm messing with my own head today. The norm.distribution is always a cumulative function, so it always gives us the area to the left of something, below something. So if we have a test statistic that is positive, is on the high side, as we do in this case, then the norm.distribution function is going to give us the probability of being below that, and that's not what we want. we always, when we're doing hypothesis testing, we want to know the probability of being as far away from the center or farther as our z-stat, right? So our z-stat of 2.8 tells us that we're roughly 2.8 standard deviations above the mean, and the mean of our standard normal is always 0, right? So the differences that we see between these two groups is roughly 2.8 standard deviations above 0. And so the probability of that happening, the p-value, is the area above that, the area in the tail of the z-curve that is beyond that, that's further from the middle. Well, the norm.distribution function is only going to give us the area below it, the area to the left. So that's why we have to do equals 1 minus. We have to take the complement of that. So if we always do equals 1 minus the norm.distribution, that's always going to give us the area to the right, right, above whatever z-stat we have. Well, what happens if we had switched the data in these two columns? Then our sample difference would have been negative, right? Because we would have had the bigger things. So instead of having an average of 9.8 for sample 1 and 6.7 for sample 2, these would have switched. And then we would have had a negative 3. And then this would have been a negative z-stat. Would have been the exact same thing. It just would have been negative 2.8. And then, if we did 1 minus it, everything would have been wrong, right? Because the norm.distribution would give us the area below that negative number, which is what we actually want, because if we have a negative number, it's down on the left-hand side of our tail. And then doing 1 minus it, of course, would now give us the area above it, and then everything would be wrong. So in order to have to, to avoid having to figure out, well, when it's a negative, I do this, and when it's a positive, I do that, we just take the absolute value of our z-stat. So that's why up here we have absolute value of T10. So if we had done a switcheroo and our samples were in the opposite place and we got a negative z-stat, taking the absolute value of it would get us back to a positive z-stat. Then the norm.distribution would give us the area below it, which is what we don't want. So then we would do 1 minus that to get the complement to get the stuff above it. Now I know that sounds like we're doing a lot of extra steps, but we're doing this so that we can always get the correct answer for any scenario. No matter what our data is, no matter what our z-stat is, we will always get the correct p-value for a one-tailed test, and then the two-tailed test is simple. All you do is double it, right? Because whatever the probability of being as far from the center as you are with whatever your z-stat is, you're just taking the corresponding congruent, right, same shaped tail on the other side, because our z distribution is symmetrical. So you're just basically doubling it. So that's where you get the one tail versus two tail. Two tail is simply you just multiply by 2. And so this is now set up to tackle any of these things whatsoever. Now, just to kind of highlight what I'm talking about as far as how this works, let me switch places with these, right? So put this one here, move this one over here, and put this one back over here. You can see that now my difference is negative 3.1667. My z-stat is just negative 2.8, blah, 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 blah. And my p-value is still the exact same thing, the 0.00248. So that's why we do this. It's to get us an accurate p-value for any scenario, whether the first sample has a bigger mean than the second sample or vice versa. We're still going to get an accurate answer if we always do the complement of the absolute value. The absolute value will always give us a positive z, and then we want area above that positive z-score. The norm.distribution gives us the area below it, so if we do 1 minus, we're now always getting the area above a positive z-score. Why do we have 0, 1, and true? Well, the way the norm.distribution function works, as you can see down here, first you give it your x value, or in this case our z-score. Then you give it the mean and standard deviation of your sample distribution. Since we're doing z-scores, we're on the standard normal z distribution, and the standard normal z distribution has a mean of 0 and a standard deviation of 1. And then cumulative just means, do we actually want all of the area below it? Yes, we do. So that's why we do true. Okay, so that's how it works.